All right, thank you, Justin, and thanks everyone for coming. I'm excited to talk to everyone about kind of just some different signals that give us clues as to why or where magma is moving from and to in underneath Kilauea Volcano. So let's see. All right, so just a basic background. Kilauea is not your mother's stratovolcano. It is not this big giant cone where magma typically comes out of the top of the cone. One of the really interesting things about Kilauea is that it involves these two rift zones. And in fact, that's a feature of most Hawaiian volcanoes in their shield stage, is that they will have these long cracks in the crust from which eruptions can and do occur quite frequently. And so we'll talk about the exact geometry of magma movement later on, but really, magma essentially comes up underneath the summit and then moves at shallow levels in the crust out into the rift zones and can erupt anywhere several tens of kilometers away from the summit area. And in our case at Kilauea, the east rift zone is by far the most active place. It is far preferred over the southwest rift zone. And in fact, we'll talk about an eruption on the east rift zone today. So, we can look at a map. We can kind of, talk about what this looks like. If we look at it from the air, we can see this is a view back toward the summit of Kilauea from PU'U, and you can see that there's not a giant stratovolcano, or there's not a big cone that sort of shows where magma's typically coming out of. So we're looking back from PU'U, which started erupting in 1983 and has more or less been continuously erupting since. You can see that there's a summit vent where magma sort of makes it to shallow levels in the crust initially. That vent hosts a lava lake and started in 2008. And then you can see that this is basically about 20 kilometers here between PU'U and the summit. And you can see back behind there is Mauna Loa, which is really just an incredibly large feature. And we'll be talking about Kilauea today, but even Mauna Loa is showing signs of unrest right now. So speaking of the summit area, this is the summit lava lake. This is an infrared time-lapse image. So this is going to show several years of lava lake activity. And what I want you to notice is that the lava lake is basically, it's very dynamic. It doesn't just sit there. The level is increasing, it's decreasing, it's changing shape. The magma conduit, as it is right at the top there, is changing. The shape of the overall pit is changing. The ledge that's on the sort of the lower left there is changing. So it's not just sitting there doing its thing since 2008. It is actually fairly dynamic, and I think a lot of these changes are probably affecting some of the signals that we're seeing seismogenically, which is interesting, but sort of outside of what I'm going to talk about directly today. We're not going to talk about dynamic changes in the lava lake necessarily, but you can see that the lava level comes up, it goes down, and really that this has been sort of thought of as a really nice way to track what the pressure is in the summit area. When the summit lava lake is high, we're seeing high pressures. When it's low, we're seeing relatively low pressures. If we go out to PU'U, this is what it looks like. You can see here that there's a couple of remnants of spatter cones from the early 80s and mid 80s out here. In large part, those have been paved over by lava flows that have come from the middle. if you look in the, if you kind of look closely as to where the steam is rising from there, you'll see little hornitos, you'll see little lava flows inside the vent area there. And then lava basically flows out of here. It may flow on the surface. More often than not, it forms a tube that runs down. Sometimes it runs down toward towns like PU'U. That was a crisis that happened rather recently, where lava was sort of moving in and potentially endangering a little village down there. But more often than not, it basically peels off toward the ocean and creates an ocean entry. And more recently has been an area where we've seen a lot of collapse of that delta that's been built up from the lava hitting the ocean and sort of piling up. So here's the bad news. At Kilauea, and indeed at most volcanoes, magma is constantly moving in many parts of the crust, but the seismic signals are sparse. So basically what you can see here is a helicorder. I think most people on this call or on this webinar know how to read a helicorder. But basically you read it like a book from upper left to lower right. And in this case, we've got 30 minutes are represented in each line. And you can see there are several earthquakes here. These are these high amplitude transients. This is a single station that's right on top of the magma pathway out in the East Rift Zone. And you see some earthquakes here. Well, these earthquakes are, almost all of them are not from the area close to this station. They're from other parts of the island. In fact, the only earthquake that happened in this 24-hour record here is that one right there. That small earthquake is the only earthquake that happened in this particular area. Now, during the 24 hours of this record, based on whatever estimate you want to take, somewhere between 300,000 and 500,000 cubic meters of magma flowed through the conduit, and yet here we are with a single earthquake to work with. So in a lot of cases, magma moving through the crust can do so fairly silently, especially in open systems. But it's also the case in closed systems as well. So here's the most updated view of the magma pathways underneath Kilauea. Basically what you have is you have Kilauea summit up here, and you have essentially a vertical conduit that goes down. And we've got two magma chambers. We've got one magma chamber under the summit, the MAKAOPUHI chamber, that is about 1.5 kilometers or 2 kilometers below the surface. Below that, we've got a much larger magma chamber, the South Caldera magma chamber. And then emanating from those are a set of conduits that feed the East Rift Zone, the Southwest Rift Zone. And what's interesting to note is that these are actually, this is actually occurring at pretty shallow levels. So somewhere between 2 and 3 kilometers is where we think the conduit comes out of the summit system and starts feeding the East Rift and potentially the Southwest, the Southwest Rift Zone. Now we get this from, all kinds of things, mostly GPS, tilt, and the earthquake catalog, although in part the eruptive history plays some role as well. What's interesting to note here, and something we are going to talk about, is that there's not a lot of detail. We don't know a lot of what's going on below 10 kilometers. It's an area that is much less seismically active, so we have fewer clues as to what's going on. It's a depth that it's hard for GPS to really light up, because you really need a very large transient in order to pick it up on a GPS sensor at the surface. And so down below, about 10 kilometers below the surface, it gets a little shaky. And again, we'll talk about that in just a second here. So let's talk about those areas that are sort of down below that 10-kilometer depth. There are these really interesting signals, And again, we have a helicorder on the left. This is a station that is basically, if you look on the map on the right, the arrow basically points to where this station is. It is about 45 kilometers to the south and west of the summit of Kilauea, which sits right up here. What we see here is we see these long duration signals. They have some high amplitude transients in them, and indeed, when you zoom in on these, there are some pickable earthquakes in there. So we can locate those. We can get PNS waves on some of these earthquakes that are embedded within this tremor signal. And when we do that, we find that we get lots of earthquakes that are around basically 30 kilometers or deeper. And so the earthquakes that are embedded in this tremor are occurring basically within the upper mantle. And they're happening all the time, quite frequently, and they're occurring 45 kilometers to sort of the southwest of the summit of Kilauea. You know, so we want to work with these tremor signals. Having the earthquakes is nice, but there's also information in the tremor itself. So basically, Aaron Weck and I went to graduate school together, and so I knew about his ability to locate non-volcanic tremor, the Cascade subduction zone. So we sort of adapted this to the system in Hawaii, and used a bunch of different subnets. This is one example of a subnet that we were using for calibrating what we were doing here. And so this is the Kilauea summit area. The triangles are the stations that we're using. And basically what we see in the summit is we see a lot of tremor that's associated with the spattering of the lava lake. And so in map view, the lava lake sits right about here. And so we would expect if the tremor locations were working properly, we would expect that they would localize back to that area. This is an example of the results of those tremor locations, and in fact, they do localize pretty well right around the spattering source of the lava lake. And so we think that we're doing a pretty good job, at least in this case, of localizing that tremor. So now we sort of let it loose on a subnet that looks like this. So if you look in the upper left figure here, the yellow stations are the stations that we're using to both detect tremor and locate it. And basically the box that's there that's sort of oriented 45 degrees is the area in which we sort of accept locations from that particular subnet. So we're trying to reduce the amount or the number of little triggers or things that we get from outside that box. We're really sort of focused in on this area that has these deep earthquakes. And you know what you see is you see a bunch of red dots here, you see a bunch of blue dots around the summit. We can kind of you know, we can summarize that by saying, okay, well, we're seeing a bunch of deep tremor here in this red outline, and we're seeing a bunch of shallow long period earthquakes up here in this blue. We expect to see the shallow long period earthquakes because that's where the lava lake is. What's interesting is that there's not really, you know, there are a few dots that show up here. When we go back and QC those, we find that those are anomalous. And so basically what we're seeing is that where there's no tremor and there's no long period events that are occurring between the summit and this deep tremor. When we look at the distribution of the deep tremor, again, the red blotch here, when we look at that in time, what we find is that overall the rates, and this is for several years of record, we find that there are short-term increases in the number of events that we detect per day, and that is number of events of tremor. But overall, the rate is fairly steady through time. So what do these things look like? You know, when you look at these shallow LP events, and you take this little gray box here, here's the spectra. The dark is the noise spectra, and the blue basically. So what we're seeing with the shallow LP events is lots of energy down below 5 hertz. The deep tremor, if we take we take a box here, and again, this is much longer record than what we show in the blue record here. But we have the spectra here, and you can see that we have lots of energy above. You know, really, we have lots of energy all the way between 0 and 20 hertz. And again, the dark here is the noise spectra. But you can see that the tremor consists of lots of frequencies that far and away exceed the bandwidth of the LP events. Also, there's a little earthquake here, and probably another little earthquake here. When we zoom into those earthquakes, you can see that these deep earthquakes, basically there's a P that you could pick here, and then there's an S that occurs a little later on. And again, this is the spectra of that, and it has a lot of similarities to this deep tremor in that it's sort of, there's 2 main peaks, one between 0 and 10 hertz, and another one between 10 and 20 hertz, maybe a little stronger in the high frequencies. We compare all these together. You know, again, we sort of find when we take the high frequencies against the low frequencies, we can create a frequency index, and we can see that basically the red deep tremor and the yellow deep earthquakes sort of overlap in their frequency content. Another interesting observation here is that there tends to be a lot of persistent seismicity at 30 kilometers deep that spans this blue region that we detect the shallow long period earthquakes in, and the red region where we detect the deep tremor. And so what I'm showing here is earthquakes that are greater than 25 kilometers deep. And there's a lot of earthquakes in here that are basically right around that 30 kilometer deep range. Now, these are regular volcano-tectonic earthquakes. So they look for all the world like just a regular tectonic earthquake. There are no recognized low frequency earthquakes in there. And other authors have seen this, they've looked at it, they've analyzed it, and basically said that this forms what's essentially a nearly flat mantle fault zone. And so basically when you look at this in cross section, all these earthquakes kind of line up at right around 30 kilometers. And that sort of spans this area between the deep LP, between the shallow LPs and the deep tremor. So when we look at this in cross section, we take some relative relocation. So that's the gray here from another study by Matosa et al. Here's our detections of the long period, shallow long period events in blue. Here's our tremor in red. And then we've got the tremor quakes, which tend to locate above those tremor locations. And so you can kind of see here in this histogram on the right, you can see that the tremor is sort of the deepest expression that we see of some sort of seismic energy release. And then above that is tremor earthquakes. And then above that, right at around 30 kilometers, is the mantle fault zone earthquakes. And so again, this is sort of schematically down here at the bottom, we have deep tremor, possibly coming from a mantle plume that trends into tremor quakes, and then kind of meets this mantle fault zone, which spans this area, and in a sense spans the area between what's going on here in this deep tremor and what's going on here in the shallow long period detections at Kilauea itself. We would, we would follow some other authors' interpretations from some earthquakes that were off to the east in previous studies, and say that basically we think that the pathway of magma movement goes from the mantle plume here and trends from deep tremor. The next expression is this tremor quake, and then magma basically moves along this mantle fault zone until it gets underneath Kilauea, and then moves basically vertically from 30 kilometers up to the summit of Kilauea. So we were able to use Aaron Weck's tremor codes adapted from the non-volcanic tremor environment and adapt that for all of Hawaii. And we started running this in real time, or near real time, at Hawaii. And what we ended up finding is that we actually started seeing some things that we hadn't seen before. And so there's some likely culprits here. You know, what you find when you start running this over a long period of time is that not only does it really pick up tremor well, but it also picks up little tiny earthquakes and larger earthquakes as well. But we basically can filter out, we can look against the catalog that the Hawaii Volcano Observatory makes. We can compare it against that and take out anything that's already in the catalog. What we're left with is a bunch of little earthquakes as well. And so here's Mauna Loa. You can see there's a bunch of little earthquakes that are here. When you look at those individually, they're little, you know, basically regular tectonic earthquakes. We see lots of detections here around Kilauea. This is with the lava lake. This is a little swarm. Then when you look across time, you start seeing these things that are going on up here, and these really aren't represented very well in the catalog. And so this has actually become a source of further study, and Aaron and I are working on what these earthquakes actually are. They're quite fascinating, but it sort of goes to show you what these you know, what can come out of just running a locator and detector like this over a long period of time. We're finding events that aren't really represented in the catalog and getting new understandings of what's happening. So let's move from the deepest part of the system. Now we're going to move to more of a shallow part of the system. We're going to go into the East Rift Zone, and we're going to move from, say, 50 kilometers. Now we're coming back up, and we're going to go to about 3 kilometers deep. And so basically, when I got to Hawaii Volcano Observatory, the day that I arrived in Hawaii, the KAMOAMOA eruption started, and this started a series of 3 different, what we call episodes, which are sort of, you can think of them as chapters in the book of the PU'U eruption. So this is called episode 59. It also has a name. It was called the KAMOAMOA eruption. This is what that looks like, that fissure, and then that fissure was feeding lava flows, in this case, that were going down here toward the ocean, but also into this giant crack. This is what it looked like at PU'U. You can see there's lava flows on the top there, and it looks actually fairly stable. This had been sort of going on for quite some time, and then the bottom basically falls out of the pit there. And so obviously, while it looked stable on top, obviously there was some sort of balloon of sort of hot magma that was happening under the surface. And when we looked just uprift, essentially this is what it looked like. There was a fissure popping out. And basically your standard curtain of fire that basically over the course of a couple of days came down to sort of one vent that was feeding lava flows, and then a couple of days later it ended. Right after it ended, basically flow was restored to PU'U, and there was a lava lake at PU'U. And so this is what it looked like. This is a thermal infrared over the course of several days. You can see that it was inflating, and the lava lake was building within the cone. And then basically the force of, or the load of that basically exceeded the strength of the cone, and it basically did the exact same thing that it did in 59, which is where it basically collapsed, and now that lava basically ran somewhere else. And in this case, it didn't have this big fissure eruption. It basically erupted out of sill on the side of the cone and fed this area here. So this is PU'U where we were looking just a second ago, and then this is the new flow here, which actually erupted at quite a high rate. So this is sort of abnormal for Hawaiian lava flows, which tend to flow fairly slowly. This one, because it was draining that lava lake at the surface, actually flowed rather quickly, and it would not have worked out well for you if you were working in the field in this area and had to get away from this lava flow. Again, here's Halima'uma'u pathway. East Rift Zone goes this way, kind of rotates up here, and PU'U, although not represented in this DEM, kind of sits right here. This is where this is basically where we're looking, is right here. Episode 61 happened. Again, a minor collapse at the top, and then basically a lava flow came out the side. So sort of the same, kind of see the same story in 3 different episodes. And so it's interesting. We can look at the seismicity during those 3 periods, and that's what we have here. We have the summit, which is in this area. Magma basically goes down here, takes a turn, comes out this way, and erupts out in this area out here. We can see spatially that we can basically divide the seismicity up into 2 areas. One we'll call the MAKAOPUHI area, which is here because it's got the MAKAOPUHI craters in this area, and then this is the Upper East Rift. When we look through time, we've got episode 59, 60, and 61 represented with these red vertical lines here. You can see that the seismicity in terms of events per day and in terms of cumulative magnitude was much higher before the KAMOAMOA eruption than before either of the other 2 eruptions. But you can see that in the Upper East Rift there was an expression of seismicity, perhaps up to 10 events per day in both scenarios and before both eruptions. So this is definitely precursory seismicity. Although the ability for us to use that directly to figure out what was about to erupt was not that useful. At MAKAOPUHI, you can see that we have lots of earthquakes that are right before the KAMOAMOA eruption, and basically nothing after. And so there's nothing going on during the eruptions for episode 60 and 61, which again were failures out the side of the PU'U cone. So one thing that I like to do, I like to look at repeating earthquakes. This sequence was full of them. For a little introduction, repeating earthquakes occur. I sometimes call them multiplets. I'll use sort of the term interchangeably. But basically what you have to get a repeating earthquake or a multiplet is you have to have 2 earthquakes in essentially the same location with the same source mechanism. And as you move those locations further apart, that waveform can get progressively different. If you change the source mechanism slightly, that can change the waveform as well. Multiplets are present in all tectonic environments. They see them on the San Andreas, see them in swarms a lot, regular tectonic swarms. We see them on volcanoes a lot. And really, you have to have some sort of repeatable process. So fault plane destruction or significant stress changes can stop the occurrence of a multiplet. So you may have a multiplet happening again and again and again and again and again, and if you get either a large earthquake that destroys that fault plane or maybe changes the stress, or you get a dike propagating, potentially that can change the stress enough so that that multiplet will stop occurring, at least for a short time, until stress is restored or that fault plane is restored. When we look at multiplets, we oftentimes display them in this way, where we have time on the x-axis and basically kind of an arbitrary multiplet ID on the y-axis. And so every earthquake is represented by a circle, and all the circles that lie on the same line are part of a repeating earthquake sequence. So again, we have three. We're in the Upper East Rift, so we're talking about those earthquakes just to the south and east of the summit area. Here's episode 59. You can see there's lots of multiplets that are occurring. So there's not only lots of earthquakes, but lots of earthquakes that are on the same line. So that means that they're basically the same earthquake happening. And what's really interesting about this is that in a lot of cases, we actually see multiplets occur right before these eruptions, or before this eruption, and then it stops for a while, and then it reoccurs before the next one, and then it reoccurs before the next one. And we see that in a bunch of cases here. Here's another case where we see a repeating earthquake sequence start before an eruption, and then basically get turned off for a while and get turned back on right before the next sequence starts. In blue here is the event rate. You can see that the event rates, this blue line, is highly variable before breakouts in fissures, and fairly low when things aren't happening. So if we look just at the time period before the KAMOAMOA eruption, that's episode 59, we can see that indeed when there's high event rates, that there is lots of multiplets. That gives you some indication that a lot of the earthquakes that we're seeing are part of some sort of repeating sequence. In this case, there's lots of repeating sequences that are happening kind of at the same time. You know, we can compare the number of events per day to the number of multiplets. And what we can find is that most of the seismicity that's happening before these eruptions, at least in the Upper East Rift, are part of some sort of repeating sequence. They're lighting up the same fault patches and hitting those fault patches again and again and again and again. You know, a lot of multiplet sources present with high numbers of events. And so within that event, we have you know, more than 20 events on a couple of different multiplets, more than 10 events on several. And you know, if you think about what that process is, it's got to be something that's repeatable. It cannot be something where we're destroying the fault plane over and over and over again, because it would be really hard to get that source process going again. So really, we need to be slipping the same plane over and over and over again in some kind of repeatable process. I should have mentioned before that everything in the Upper East Rift is volcanotectonic. When we look at the fault plane solutions, they are actually strike slip as well. When we go and we look at the MAKAOPUHI multiplets, and I'm just zoomed in right now to that area right before the KAMOAMOA eruption, because if you remember, there weren't any multiplets that occurred after the KAMOAMOA eruption. You can see that it's pretty, you know, there are some repeating sequences that are going on here, but the rates are not very high until you get right to the eruption, and then you get a lot of families with high event rates, but very short durations. And so there's several new multiplets that are occurring. That's these things that are occurring prior to and during the eruption. You know, really, when you think about it, that's got to be, you know, that's got to be something different than what we're seeing uprift in the Upper East Rift. So, unlike the earthquakes that were in the Upper East Rift, most of the seismicity in the MAKAOPUHI area was not part of a multiplet. The multiplets that were occurring are low in numbers, especially compared to the Upper East Rift, and the recurrence intervals were really significantly higher prior to the eruption and during the eruption. So really, this is sort of what we're thinking here is that this is you know, despite also being a repeating earthquake sequence, this is something that must have been part of a destructive process, like a dike intrusion. And so maybe what we're seeing here is actually that propagation of the dike light up some multiplet patches for short times before they're destroyed by the dike sort of moving through. And that's basically what we're showing here. Again, the seismicity up here is the Upper East Rift seismicity. We see that prior to each of the episodes here, which we're showing in these 3 panels. So KAMOAMOA is up here, episode 60 is here, episode 61 is down here. Red stars are where the eruptive vent is for that eruption. So here it was at the end of this model dike from Paul Lundgren et al. Here it was out the side of PU'U's cone. And so this all sort of starts to make sense process-wise, especially the MAKAOPUHI stuff, because the MAKAOPUHI locations are really well co-located with that model dike that was modeled based on a combination of INSAR and GPS. And so the fact that that doesn't reoccur during episode 60 and 61 makes a lot of sense. It also makes a lot of sense that it would be associated with the dike intrusion, because that is a destructive process. You are changing stresses. Potentially, you're destroying fault planes, and it's a very dynamic process. Whereas what's going on up here has been it has been interpreted before by Guillard and others to be arising from basically pressurization or maybe a little bit of dilatation of the conduit that feeds the magma chamber from the summit area down into the East Rift. And a little bit of dilatation from that basically facilitates faulting above that conduit. And that's what we're seeing here with strike slip faulting along the Upper East Rift here. And again, these are all repeating earthquake sequences here and here that are actually repeating between eruptions too. So this has to be something that is in fact repeatable and isn't destroying the fault plane. So now we're going to move from, we started deep, we started looking at tremor, we got shallow, we started looking at repeating earthquakes. Now we're going to get into the shallowest part of the system. We're going to look at the lava lake. And we're going to, here's a video of the lava lake. You're going to see that's basically a part of the lava, a wall of the pit there falling into the lava lake surface and creating basically a seiche in the lava lake surface. I'll run that one more time because it's short. It comes off the right-hand side there. You can see that piece comes off. There's a little bit of an explosion, and then basically you're getting a lot of movement of the surface of that lava lake. If you look from above, this is looking as at night, so you're looking toward the lava, or toward the pit here. The lava lake surface actually sits below where you can see, but you can see that there's a illuminated area here. This is where the spattering occurs in the lava lake, and you can see when this thing falls in, boom, you get a nice explosion that comes out, obviously making quite a nice infrasound signal in addition to a seismic signal. This is kind of what it looks like. And this is another example from Tremor et al. Here's rockfall coming off the lava lake surface, and then you can see the explosion that occurs. Probably, you know, you're agitating that surface, you're creating areas for gas to nucleate out of the out of solution there, and you're getting a violent explosion that's impacting that particular area right there. Seismically, it's really interesting. You get a combination of high frequency signals, which are kind of small. You can start to see them here. This is sort of the signal of rockfall, and then you get a long period signal, which is probably either bubble bursting, could be the seiche in the lava lake, and then you get a really long, very long period expression, which is around 60 seconds or so. Which is, you know, really at those to generate a wavelength that long, really you need to sort of be incorporating the entire conduit, or at least the shallow conduit structure. And so you're seeing we call these composite events because they're really combining a combination of high frequency, low frequency, and very long period energies all into one event. Again, we see some of the very long period earthquakes. We see a lot of them from these rock falls. We also see them without any occurrence of rock falls. So there's a couple different ways to goose the system to get these very long period earthquakes. Interestingly, we wanted to look at the tilt that was coming from these. Many of you know that broadbands have a sensitivity to tilt. Oftentimes that's thought of as a noise signal. We actually really like it. We wanted to use this tilt signal to better constrain what was going on in the volcano. But also, tilt meters are really hard to install. You have to drill a borehole. Seismometers are relatively easy. We already had broadband seismometers out there that we could use. And again, or I should say that here on top is sort of the response, velocity response of a broadband, just sort of a generic 120-second broadband. And you can see that the velocity response falls off. Actually, maybe it's, and as the velocity falls off, the tilt, the sensitivity to tilt actually picks up. And then there's this area in the middle here that is where sort of the tilt and the translation are kind of together. So this is the existing tilt meter network. It's a little hard to see. There's these green dots here. There's 4 tilt meters. Notice that there's none inside the caldera here. This is a no dig area because it is culturally sensitive for the Hawaiian culture there, so you cannot drill. And so there aren't any tilt meters. They're basically the same distance apart, and they're of varying quality too. A lot of times the Iki and the summer camp tilt meter here have really large diurnal signals. If you look at the seismometers, now you've got these white things here. We've got surface mount seismometers in this case that are 10 of them that are around the caldera. So if we can pull the tilt meter, or if we can pull tilt out of these and incorporate that into the tilt meter records, then we might be able to do something to constrain what's going on at the volcano. So we can basically calibrate what we're doing tilt-wise and figure out whether or not we've whether or not we're doing this right. So you can see here, this is 2 shots of the lava lake. It's on the left, it's sort of spattering along as normal. And then there's rockfall that comes off the left. And so actually there were 2 rockfalls. And we can basically try to figure out if we're getting the tilt out of that correctly. Cut to the chase here. The blue signal is the tilt meter record from UA. There's a couple of co-located tilt meter and broadbands, and so the blue basically shows a single rockfall here just after 120 minutes, and then again at 150 minutes. And so this is the east tilt, and the red is what we've is sort of a low pass filtered version of what we were able to derive from the broadband. And so what you can see is that we are recovering the tilt, the long period tilt from the tilt meter very well for these 2 rockfalls. And we get the amplitude right, we get the sign right. And here's the north tilt. Maybe we don't quite get the amplitude right right before the rockfall here, but you can see that we do get the right sign and most of the right amplitude for both those rockfalls. So the transform's working. When we pull this to the network-wide conversion, when we basically do this for the whole network, we find that basically the tilt points back toward a source that's north of the Summit lava lake here. This basically points back to where the Halemaumau chamber is at 1.5 kilometers or 2 kilometers deep here. There are some cases where we get some really weird tilt signals, and a lot of this comes down to the quality of the installation. And so that if the quality of the installation is not as good, it's hard to recover that tilt. So we wanted to kind of push it a little further. We wanted to kind of see just how much tilt we could recover. So there are these transients at Kilauea. They're called deflation-inflation events. And so basically over the course of several hours to days, the tilt will actually rise and fall, and rise and fall and rise and fall. And it's been doing this for quite a while. And we see this on all the tilt meters that are around the summit area. The lava lake changes with the rise and fall in tilt. So we get a high lava lake level when we get relatively high tilts, and low lava lake levels when we get low tilts. That's shown here. The GPS is not as sensitive to it. It's largely vertical, and so but the strain does see these deflation-inflation events as well. Interestingly, there's also the deflation-inflation events are variably reflected at PU'U, which suggests conductivity. But interestingly, they're not always reflected in the change in, or the lag time in when they're reflected at PU'U changes. So when we apply our transforms to our broadband to tilt transform to those deflation-inflation events, this is what we see. So it's a little messy. Basically, we've got a long record of tilt here. This is about 7 days. And what you can see is that you can see in red here is UA, and this is the inflation deflation. So here's the inflation. This is a real tilt meter. Inflation, deflation, inflation. Here's North Pit, which is right on top of the source. So we should expect to see a much larger signal there. And we get inflation where we get inflation on UA. We get deflation where we get deflation, and then we get back inflation. Now you can see that there's diurnal signals that are also within this signal as well, but we are recovering the overall inflation deflation signal. At KKO, it is on the other side of the it's on the other side of the source, and so the tilt is opposite signs, or is an opposite sign. So you can see it basically sees deflation and then inflation and deflation. So that's what we would expect. Not a lot of diurnals in there. The vault is quite good. At Sand Hill, again, you see these big diurnal signals, but it is recovering the deflation-inflation signal quite well. And again, this is a 7-day record. So really, this was astonishing to us. We really had no idea that we would be able to recover tilts along this long of a baseline. Well, who cares? Well, turns out when you go to model these things with tilt, it really better constrains what they're able to model. So these are models run from Kyle Anderson. These are Monte Carlo simulations of basically tilt tilt sources. And so what we're showing is the east position, the north position, depth, and basically the change in volume. And red is, or actually I should start, the blue is what is just with the tilt network, and the red is what are basically broadband observations add to that model. And in all cases, what you can see is that the tilt source is better constrained with the addition of these broadband sensors, partly because at least North Pit and KKO are new radiuses. So they're in different radiuses than the existing tilt meter network, but also North Pit is right on top of it. So it really helps constrain especially the depth, which is very poorly constrained with the existing tilt meter network, the north position, and the volume. And so that all changes with respect to, or just by adding in these broadband sensors. And so that gives us a better sense of the source of the tilt, and we can actually start going from a MOGI source in this point, and we're going to start moving toward more realistic sources and actually figure out what that magma chamber potentially looks like. There's also a real-time application here. We wanted to try to figure out if we could use this in real time. So basically in black is the tilt meter record. So this is the real tilt meter record. The red is the transform that we've been showing up till now. You can see there's a transient here. And so basically, again, our normal transform is recovering that tilt signal pretty well. And then we wanted to do, basically, we wanted to try to introduce a recursive seismic tilt so that we could basically do the tilt transform in real time and potentially add those tilt observations to the existing tilt record as it's coming in. So much in the way that seismic data is recursively filtered, we'd like to try to do that with tilt. The problem is, in this case, is in order to for the filter to be stable, we needed to introduce a high-pass filter that gets rid of some of these longer period signals. So there may be some application here, but it's only going to really recover sort of really short-term tilt transients, which in the case of a volcano is there are realistic sources, dike intrusions and such that this could feed into. So I'll wrap that up. Thank you for listening and attending. I'll finish up with just the fact that earthquakes are uniquely useful, and that it's not just regular volcanotectonic earthquakes. There's a lot of information in the noise and in the strange signals that are typically ignored that can give us more insights into what is going on in the volcanic system, even for systems that are fairly well studied like Kilauea. And I'll end it there and hand it back to Justin.
Great, thanks Wes. Thanks for a really intriguing talk. If folks out there listening do have questions, feel free to send those in. We have time for maybe just a couple questions. We did have one come in during your talk, Wes, about the tremor that you were showing in the early part of your talk, and they wanted to know what the amount of tremor over time would look like if you used moment or some other kind of measure rather than just strictly counting the number of tremor events. Have you done an analysis like that?
Yeah, that's a great question. And with tremor, there's not a very good scaling of magnitude or regular earthquake magnitude. So a lot of times what we'll use is something called reduced displacement. And basically we find that the reduced displacement basically follows the same trend as the number of events. So obviously, you're getting releases. There is some swarminess to it, but overall, when you look over the time span of years to decade scale stuff, which we've done and others have done, it's really pretty constant through time.
Okay. Another question, just wanting a bit more detail about your estimation of tilt from seismometers. Do you use all three components, only vertical? Maybe just a bit more detail on that.
Yeah, so we use all three components, and basically well, no, wait, is that true? Let's see, it's been a while since I've done this tilt transform. So no, I think that we only actually use the north and the east, and we just apply basically a set of filters to it to get that north and east tilt. And then, yeah, so that's correct. Sorry, it took me a little bit to rack my brain to figure out exactly what we were doing there. So yeah, we're really just looking at the north and the east. But We do use, and I didn't show it here, but I was working with Matt Haney on this, and he was using more of the signal to get at what the translation actually was, or what trying to tease apart that part of the spectra where the tilt and the velocity basically overlap. And so he was using all three components, if I remember correctly, to get at what portion of that was velocity and what portion of that was tilt.
Has your tilt analysis, has any of that work been published as yet, Wes?
It's something we're still trying to find time to work up right now. So we've presented it at a couple of conferences, but we have not gotten a chance to get it actually formally written up. Although the transform has been written up by John Lyons on a, I think it was on Fuego volcano, although I could be wrong. It was there was a volcano in either Central or South America that John Lyons did this sort of transform on, and that got me interested in it, and so we brought him over to Kilauea.
All right, one last question here. This is with regards to the earthquakes that you were showing. Do you have, I don't know if this is something you touched on, but any estimate of focal mechanisms for either the deep events in the mantle or the shallower events?
So the deepest events we have no focal mechanisms for. So like the stuff at 50 kilometers, the distribution of stations is all one-sided. It's really a mess, and polarities are very difficult. The signals are too high frequency to really. We just don't understand the. Well, for one, we can't get polarities on them because a lot of times they're buried in the tremor. For two, we're all on one side of the earthquake because we're only on shore. And then three, we'd like to do something like a moment tensor, like a waveform modeling, but these things are too high frequency. They don't have any low frequency content in order to get at, or well, we'd have to go to higher frequencies than we have resolution for the velocity model. So moment tensors are hard for those deeper events. The mantle fault zone events typically have basically flat focal mechanisms. So basically the fault plane is essentially flat. I'm not sure if the person who asked this was also interested in the East Rift Zone earthquakes, but I have a slide on those there. So that's what the East Rift earthquakes look like, strike slip, and then we've got kind of a plethora of different focal mechanisms for that MAKAOPUHI stuff.
All right, great. Thanks, Wes. We had a couple other questions come in, but in the interest of time, I think I'm going to go ahead and end the webinar here. But Wes, what I can do is go ahead and bounce these questions along to you. For folks out there listening, if you have additional questions, I would encourage you to just shoot Wes an email if you've got things you want to follow up with him on. I know looks like we've had a lot of really great questions come in on this talk. So thanks again to our presenter, Wes Thelen, today, and thanks to you all for tuning in.
Yeah, thanks. And you can always get my email just by looking up my profile page. Just type in Weston Thelen USGS, and I'll be the first link.
Thanks, Wes.